Hello everyone and welcome back. In the previous parts, we've looked at the Metasploit obfuscations and understood how the payload works. In this video, we'll reverse engineer a very important component of the shellcode, which is function resolution. We've seen that there are a lot of imported functions and some of them, they actually make sense. For example, the functions from WinSock32 library, because we know the binary makes network calls. Let's look again at one of those names and check if it's ever used. Use X to see cross-references. There is one. But notice here, the cross-reference is actually in a portion which is dead code. These instructions here are never executed. They will always be skipped by this jump. This is another interesting trick of Metasploit to generate imports. Never use them, but scatter them throughout the code to make the program seem legitimate. Okay. So if the functions are not called like this, how are they actually called? Let's see. Metasploit uses a technique also known as find by hash, in which function names are hashed using specific algorithms, and then they are resolved dynamically. The dynamic resolution happens in a few simple steps. First, the shellcode needs to locate the address of kernel32.dll library, which is present in the list of loaded modules for all the applications. Next, from kernel32.dll, it will find the address of load library and use load library function to load additional modules. From those modules, it will locate any functions needed. Right in the beginning of the start function, the instructions starting from here perform function resolution. We'll deep dive into this in a moment. The first place where a function is called dynamically is in function 1. And notice that it's pretty tricky. We have a lot of junk code and a lot of unneeded instructions, a lot of jumps to obfuscate the flow. Basically, before the call to EBP, which does the function resolution, we have parameters pushed on the stack. For example, this one, which looks like a double word, looks like a hash, then 0, ESI, another very interesting value, another value here, and so on. This one over here is the most important because it represents the hash of the function to be called. To see what is behind this hash, we need to go back and look at the algorithm. So the function resolution starts from here. The code is pretty obfuscated, but we can, even with all these jumps and that code, we can quickly spot interesting stuff. Like, for example, the parsing of PEB, process environment block, over here as well, then interesting parts like loading module names. Before delving into the shellcode itself, which is pretty long, let's discuss our approach. We have actually at least 3 options. First option is, as we started here, to continue with static analysis and understand the assembly code. This is doable. The second option is to add breakpoints in key areas, like this one over here, and run the application and see what happens. The third option is to look at Metasploit payload source code. The great advantage of this is that the payload will not be obfuscated. So we won't have to deal with all this junk code. All of these flow obfuscations and junks are added dynamically by the encoder. In this video, we'll start with the second option, dynamic analysis. It will be quicker and easy to understand. I've already annotated this IDA Pro database heavily and added lots of breakpoints. For example, this part over here deals with resolving module names into the ESI register. If we go into ESI, we have here the first module in the list, which is payload.bin, the name of the executable itself. This is a Unicode string. When converted, we have payload.bin. Then a hash value of the module name is computed. Then we have another portion of the code which computes hashes for function names. For example, if we re-enable this breakpoint, enable it here, we've skipped to the next module in the list, which is probably ntdll.dll. Then a hash of this module. And then iterate through each function in each module. Let's see which is the first one. The first one is wcstool, which, by the way, converts wide C strings to unsigned longs. Basically, a hash will be computed for each function. And if that hash matches the hash we've seen before, then the code will jump to the function and execute it. We can disable this breakpoint because otherwise it will break for all the functions in the module, which are quite a lot. Execute it a few times. Notice we've now reached another function, and so on. We will disable this one also for now. Disable. Then the last module in the list, which is kernel32.dll. And at the end of the execution of the shellcode, we should have a match of the function with the hash we've seen before. If we want to know which function it is, we can skip through this code a little and pass over these instructions. Let's see. At this point, we see the function over here, which is virtual alloc. If we skip to the end of this shellcode, we should reach the point where virtual alloc is called, which should be very close. This is the jump that will take us to virtual alloc, and already we have the parameters on the stack. exactly as expected. Go back to the place where virtual alloc was called. It's actually this one here. So in order to resolve this hash value to a function name, I got some Python code. We don't care about the functions that compute the hash for now. We'll analyze them in the next video. If we know the algorithm from the code, we can generate a mapping between these hashes and function names. Let's run it. After that, we'll have 3 header files generated for these three libraries that are loaded: kernel32, ntdll, and an additional one which we'll need later. At this point, we can load these header files using load file, parse header file, and then let's load kernel32 and ntdll. And then we can map this constant to function name. We will see in the next part what is the actual algorithm and how to do the resolution. Awesome! To recap, in this video, we've discussed the find by hash technique used to dynamically load and execute functions. Stay tuned for the next part where we will deep dive into the hashing algorithm. Thank you for watching and please send your comments below. Cheers!